Hi, it's time for another math easy solution. Today we're going to discuss further into trigonometric substitution, but now take a step back and explain further in what I mean by one-to-one functions when defining when using trig substitutions. Basically, in my earlier videos, I went over an introduction to trig substitution as well as some examples, but I didn't explain in too much detail why when using trig substitution the function needs to be defined on a domain to ensure that the function is one-to-one. I'll get to this further. Basically, I also went over this table of trig substitutions. For example, if we have the expression square root a squared minus x squared inside the integral, then we could use this trig substitution, x equals a sine theta, where theta is restricted on this domain pi over 2. Yeah, it's less than or equal to pi over 2 or greater than or equal to negative pi over 2. And this base, or like all of these right here, these restrictions, they ensure that the function is one-to-one, or that x and this right here is one-to-one to each other, so that one value of theta will get one value of x right there. And also this identity is what we'll use in the trig substitution. And for example, basically, for example, if we have something like this, integral of a squared minus x squared dx, then we could apply this trig substitution. Now, to understand why we need to restrict theta like this over here to ensure that the trig function is one-to-one, we need to take a closer look at the expression and its corresponding trig substitution. Also, in this table, if you had an expression like this, you would apply, well, this substitution with this restricted domain, and then for this one, you'll have this one. I'll cover these all soon. So when we take a closer look at this, let's look at the first case, which is, we'll call this one right here the first case. So when we have a square root a squared minus x squared. Yeah, so when we look at this first case, if we were to draw a graph like this, where this y function, or the y-axis, we'll write this as the first case. So square root a squared minus x squared. So in this point, when, let's say, when x is equal to 0, then this just cancels out, and we're left with, well, a is the top. So this will just be square root a squared, which is a. If x is equal to, well, a plus or minus, because there's a square there, if it's equal to a, then this whole thing would just be, yeah, this just cancels out. You'll have an a squared minus a squared, which is 0. Likewise for negative a. So then it will end up being just a half circle like this. So we get it like this. That's how it's going to look like. And where the domain in this case is going to be like this, where x is greater than or equal to negative a and less than or equal to, well, a. And now because it's restricted on, this x is restricted between these 2 points, then it's useful to apply the trig substitution x equals to a sine theta. And the reason for this is because of the way sine theta is defined. Yeah, so now if we were to graph this on here, so if we have theta right here and graph it with x, so that's why I drew this x really long. So here's a second axis there, which is theta. So when theta is 0, well, this x is just 0. This is just basically just a sine curve. So a sine curve will look just something like that. And notice how this is just looks a bit different from the regular one because I just flipped it. This is going up, so that's positive upwards. And at this point right here, because there's an 8 multiplied by the sine, so the maximum is going to be plus a. And then the minimum here, well, that's just going to be at this point of negative a. So as you can see, when we define it here, and the reason we define it here is because we still have our domain from this case. So because right here, we're still going to get the x is less than or equal to a, greater than or equal to negative a. So we still get this, and this is the exact same thing. So that's why we can apply this trig substitution. But notice here, but notice how the way that this function is with this sign, it goes up, it goes right and left in this case because we flipped it. But So what this means is if we were to just draw just a line downwards like this, and then let's call this point x. So this point, we'll call it x. So as you can see, at this point, yeah, we get multiple values of theta. So as you can see, there's multiple values of theta, and this keeps going on and on to infinity. So we get basically infinite amount of points. Yeah, so I've written it down right here. Thus, at a point x, we get an infinite, or basically many values for theta, which we don't want, because when we have many values of theta, then we have many values for basically for sine theta, and also because we have this function right here. So what this will be is square root a squared minus, well, this is going to be an a sine theta all squared. So we get here many values. And now this is basically problematic because basically integrals and any other almost every concept in math is defined for functions that are one-to-one. Yeah, so we basically can't have many values, because then we can't write a function such as y equals f of theta, because actually I mean f of x, because basically we're going to get many values of this. So it has to be one-to-one. So it has to be one-to-one function right here. Yeah, and once again, integrals are all defined for one-to-one functions. And now, in order to do this, we need to basically restrict the domain. Yeah, and restrict the domain of theta. So if we scroll back up here, the most common one is the same for inverse functions of the inverse trig functions, and in this case it would be basically from here to here. So restricting these, so we still get our full x range or x domain, and then now we get this point right here, which is from, well, theta is less than equal to, well, this high point, this is just a sine curve, so that's pi over 2. And then right here is negative pi over 2. So this is from pi over 2, so theta is less than equal to pi over 2, and greater than equal to negative pi over 2. And when we apply this, we still have this range, so we could apply this trig substitution. Now we scroll back up here, and that's exactly what this one is using. And now for completion's sake, and also because this is pretty interesting, let's look at the second case in this table, which is when we have this square root a squared plus x squared. So if we have square root a squared plus x squared right here, and this is our x axis there. So that's the y-axis. If we were to plug in when x is 0, this just cancels right here. We'll just left with a squared, or square root of a squared, which is just a. So we'll get a right here, and since this is positive and this is x squared, anything you put in will be positive. This will just basically look like a parabola. So this will just keep going up and up, and in this case what we get is x is an element of all real numbers, or x can be basically anything. So when applying a trig substitution, and what's usually applied in this case is this case where x is equal to a tan theta, and the reason for tan, I'll get to that in a bit, is because it has some sections where this x can be all real numbers. So if I were to scroll this all the way here, so this is theta, and now we're graphing, well, tan theta, a tan theta instead of sine. So when theta is 0, we have it over here, and the curve, if you recall from my earlier videos on tan, looks something like this, where it has an asymptote line across here, where this point right here is pi over 2, and then this point right here is negative pi over 2. But once again, since this is a trig function, it just keeps repeating itself. And this point right here would just be, well, 3 pi over 2. That's right here. And it keeps repeating itself like that. oops. So something like that. So basically, as you can see, once again, we have that same problem where if you were to draw a straight line, if this is x, we get, well, multiple values of it. So we have to restrict the domain. And as you can see, in this case right here, this one is a pretty obvious where to restrict it, and then we'll just restrict it over here. Because when we restrict over here, we still get this full range. So basically x is still all real numbers inside here, and it's going to be just a one-to-one function. And also now this restriction right here, we get theta is less than equal to, actually it never touches this, it has an asymptote line, so less than pi over 2, and here is, well, greater than negative pi over 2. So if we've restricted the domain there, and we still get our x is all real numbers, which fits our function right here, or this section of the function. So when we scroll back up, as you can see, there's this restriction, it's less than and it's not equal to, and that is where we get that. And now when we look at the third case, whereas when we have this square root of x squared minus a, as opposed to this other way around. And now we'll be applying this this trig substitution x equals a secant theta, and I'll show you why we do that. So when we scroll back up here, so this is now x squared in front minus a squared. So as you can see in this one, well, whenever you have, let's say x is, or x squared is less than, I should just put x, when x is less than a, make this a better one, when x is less than a, then we get, well, a squared, actually this is, x squared is going to be, well, yeah, x squared minus a squared. What we get over here, this is going to be less than 0 because this is smaller than this one. So you're subtracting a bigger number from a smaller one. So what this means is we'll have a square root of a negative number right here. And this is, well, not a real number. So it's not a real number. So we're not defined. So yeah, basically a square root is not defined there. So it's not defined in this region right here. So we can't have x is less than a. So we can only have when x is greater or equal to a. So when x equals to a right here, these just cancel as a 0. So this is at a, and it's the same thing. I'll make this actually closer. Yeah, I'll make this a bit closer, just because we're going to have to draw it pretty far. So if that's a, and also since this is a squared, if you put a negative a, it's going to be the exact same thing on the left side though. And now when this gets bigger and bigger in positive side or negative side, this just becomes bigger and bigger. So it'll just be like that, like a parabola, like a square root function. So it expands out like that. So as you can see, we have x is defined for greater than equal to a, or at this point where x is, well, less than equal to negative a. So that's where it is defined. So now what we use for this case is the trig substitution a times secant theta, or x equals a times secant theta. And now the reason for this, once again, if we were to graph this out, this is theta. So basically this is just the flip side of cosine. So if we were to draw, well, how cosine looks like, it looks like something like this. So I'll just draw this in dashed lines. So if this is cosine, it looks something like this. So that is how cosine looks like, something like that. Where at this point we have a, because again it's a times cosine. So if this function right here is a cosine theta, and now secant, which is just the flips, it's 1 divided by cosine. So what we'll get is asymptote lines at 0, because you can't divide by 0. This is at, right here is pi over 2. Here again we'll have this asymptote line like that, and an asymptote line like this. So what we get here, yeah, this asymptote line, that's just going to be, well, 3 pi over 2, and same as over here. So what we have here now is, now we could draw our secant, And our secant, as you can see, when you're dividing close to 0, it's going to get really, really large. So we're going to be an asymptote line like that. So this is our a secant theta. But once again, it's a trig function, so you'll have repeating parts like that. And it keeps going on and on. Yeah, and then you'll have it even here as well. So we have something like this, and now what we have to do is basically, it's just a bit more tricky version of what we did in case 1 and 2. So we have to restrict the domain, because once again, if you were to draw a straight line, you're going to have one x value and then multiple values of this theta. So you can't have that. It needs to be 1 to 1, so that it's a function. It's a 1-to-1 function. You can use for integrals, etc. So now in this case, we have this restriction where x is greater than or equal to a, and x is less than or equal to a. So the reason we chose this secant theta, as you can see, on this right side we have, well, two sections, where in this case we have x is, I'll just draw it like this, x is greater than or equal to a, because as you can see there's a that's greater than or equal to it, and at this point right here this is just negative a. So, and at the left side right here is x is basically less than or equal to a, negative a. So it's less than or equal to negative a. So now all we have to do is define or restrict the domain of theta to include, one part from here and one part from here. And now the usual way that my textbook does it is actually restricts here. So it restricts basically from this point and this right here. I'll just draw it here. So this is what they restrict. You could also restrict here if you want, but the more common one is basically up top here. So when we restrict it over here, we get, well, this point right here is theta is greater than or equal to 0, because it can equal there, and now it's going to be less than pi over 2, and not equal to, just less than, because it's asymptote line. And now in this case right here we have theta is greater than or equal to, this point is actually just pi, greater than or equal to pi, and now less than 3 pi over 2. So when we restrict it to this domain, we no longer have the 1-to-1, so as you see it doesn't cut through anything. We no longer have we have a 1-to-1, we no longer have multiple points, and also we still keep this restriction right here, where this x is less than or equal to a, negative a, and x is greater than or equal to a, and which is part of this function. So we could basically use this after all in the trig substitution. So anyways, that's all for today. Hopefully you learned from this. It's pretty, this is a pretty out there tutorial. Yeah, I really wanted to go into detail of why we're using this 1-to-1 relations when we define these trig substitutions. Anyways, hopefully you learned from this video. Like always, you can download these exact notes in the link below, and also make sure to watch my earlier videos on trig substitution. Anyways, thanks for watching, and stay tuned for another math easy solution.